Hello, welcome to this section where we talk about apportionment methods. Not too long ago we talked about voting, where we were trying to figure out, who gets into office and how we're going to do that, or how we're going to make a choice, or how we're going to, like right now with the current election, you're voting on amendments and things. Some of those amendments will affect how things are divvied up, or whether you get certain funding and that kind of thing. The apportionment ties into this, because apportionment, like once you've decided, oh, we're going to have this many dollars to divvy up, apportionment decides how to divvy it up and trying to do it in as fair of a manner as possible. And there's been a lot of disagreement over the years about the best method for doing this, because often methods will favor one group over another, just with the way the mathematics, the numbers works out. So we're going to look at some big methods from our American history, the U.S. history, and we're going to look at some of the flaws and briefly touch on when they were used and what happened. All right, so the big methods we're going to look at as we try to fairly allocate numbers of items include Hamilton's method, Lowndes' method, Jefferson's method, Webster's method, and Adams's method. And many of those names might sound familiar to you if you've ever been a student of American history. And even if you haven't been a student of American history, if you're watching my video from another country right now on YouTube, you might have heard Hamilton's name at least, because right now there's a certain gentleman named Lin-Manuel Miranda who's very well known for his musical, Hamilton. And this is the same Hamilton that the musical is based on, Alexander Hamilton. So that's kind of exciting too, huh? But those are five main big methods that we are going to discuss. First, we're going to hit Hamilton's and Lowndes' methods, and then in another video, we'll hit the other three. Okay, so apportionment. The scenario I have here from another textbook is that there's a country with 200 seats in their legislature. So that in the U.S. that would be like having maybe looking at your House of Representatives and thinking about how many seats you have and how you're gonna divvy them up. Like in the U.S., the senators you have to 2 per state, but the House is based on apportionment. It's based on populations. So these apportionment methods are very important in this regard. And so this is a totally made up scenario, though, in this textbook. It's not the U.S. It's a fictional country that has 200 seats in their legislature with 5 states. And those states have these populations. We'll call them states A, B, C, D, and E. And we're going to try to figure out how many of those legislature seats each state should get based on their population. State A has 1,350,000 people. State B has 1,500,000 people. State C has 4,950,000 people. States D and E have the same number at 1,100,000. Okay, so just by looking at those populations, you could probably quickly pick out which state should get the most seats compared to the others. State C, if you don't see it already, has way more people in it than the other 4 states. States D and E should get the same number of seats since they have the same size population. State A and B might get the same number depending on how many there are to give and how it divides out. But more than likely, State B is going to have a little more than State A. And then those two will still have more than States D and E. You'll find that what happens with this all depends on how many items are being distributed and what method we use to do that distribution. Okay, so some initial formulas that are important as we start trying to figure out how to divvy up the country's 200 seats. One's called the standard divisor. That's the total population divided by the number of items to be allocated. So what are we doing with the standard divisor? We're taking how many people this country has and dividing by how many seats that we're trying to allocate. So in other words, we're trying to figure out, like for this particular country, how many people per seat. You know, if your standard divisor is like 400, then they're saying for every seat you have, that needs to represent 400 people. I'm just making up a number. I don't know what the standard divisor is yet for this scenario, but that's what's happening there. Then the standard quota is trying to get down more particularly to individual groups. So like in our country, individual states. So you take the population for that group and divide by the standard divisor. So you're saying, okay, if state A has 800,000 people, we're trying to divide that by, well, how many people per representative to see how many representatives they should get. You know, if there's supposed to be 5,000 people per representative and a state has 40,000 people, then they should get 8 representatives because they have 8 groups of 5,000 people. You know, that kind of thing. So that's what the standard divisor and the standard quota is doing for us. If we need to, we're going to work on rounding those to the hundredths place, so 2 decimal places as we go. That'll just kind of make things more consistent as we're doing examples. All right. So back to our country here. Again, you had states A, B, C, D, and E. With the 1,350,000 people, the 1,500,000 people, the 4,950,000 people, the 1,100,000 people, and I don't know the grand total yet, so I'm going to have to find that. I'm going to need it. I need to know, well, how many people total are we talking about in this country? So we're going to go ahead and add those up and see what the total population is. Because the problem didn't tell me. All right, so apparently this country has a total population of 10 million people. All right, and we had said there's 200 seats, right? So we first want to figure out, well, how many people are represented with each seat? So that's where we're going to go ahead and find our standard divisor. You'll see that I often, when I'm doing these videos as I go, now that we've talked about standard divisor, you're going to see me abbreviated SD. I'm not talking about like an SD card or anything. I'm talking about standard divisor. All right, so we have 10 million people. 10 million total people. Divided by 200 seats. And that equals 5,000 people per seat. So then we can go to each state and decide, all right, based on how many people that state has, how many seats should they get? So we see how many groups of 5,000 people they've got. So I feel like I have to keep rewriting some of this material, but A, B, C, D, E again. All right, so if state A has 1,350,000 people, then we can divide that by the 5,000 to figure out, well, how many seats should they get. So 270. I think I divided that wrong. I did. Sorry, I should just stick with using my calculating devices instead of trying to do stuff in my head. You probably already caught my mistake up above, didn't you? Ha! 10 million. See, it's talking about trying to stick with using my calculating devices. That should have been 50,000 right here. That's why that's a mess. Like, this is not making sense. Okay, so let me erase that. Yeah, okay. So divide by 50,000. Sorry about that. All right, so that gives us 27 people, or 27 reps, or seats, I should say, maybe. So I'll just be consistent and use the same wording. So 27 seats will go to state A. Because if they have 1,350,000 people, and for every 50,000 people they have, they get a seat. So if you divide by 50,000, that tells you they get 27 seats. Okay, state B had 1,500,000 people. Divide by 50,000 to see how many seats they should get. And you get 30. State C had 4,950,000 people. 50,000 people per seat. Looks like 99 seats for them. So far, this is making a lot of sense when you look at the numbers. And then states D and E had the same number. So you do the calculation on one, you'll know the calculation on the other. Okay, so you get 22 seats for each. All right, and then when you add up the numbers of seats allocated to each state, that's 200 total seats. Okay, so all 200 seats were divvied up nicely along those 5 states. So 50,000 people per seat. So that worked out pretty nicely. But in that, again, that's those numbers that we just found when we took each state's population and divided by the standard divisor. These were the standard quotas. Figuring out how many seats, when we just did that division there and got how many seats per state, we were finding the standard quota as we did that. That worked out nicely. No decimals. Doesn't always happen that way. That's where all the arguments come in. It does not always work out with no decimals like this. So that's where it gets more interesting. But at least you saw those 2 definitions. Okay. The title of this video had the words quota methods in it because the 2 methods we're going to focus on, Hamilton's and Lowndes' methods, do focus on making sure you get either the lower quota or the upper quota for your number allocated. The lower quota is the standard quota rounded down to the nearest integer. The upper quota is the standard quota rounded up to the nearest integer. So this comes into play quite a bit when you have decimals after dividing. The previous example didn't have decimals, so we didn't really have to worry about it. But if you have a decimal and you drop the decimal and just go with the integer part, that's called the lower quota. If you round up to the next integer, that's called the upper quota. And there's disagreement about which one of those should be used because of who it favors, what entities or parties it favors. All right, so let's look at the quota rule. The quota rule says that when apportioning items, the number given to each group should be either the lower quota or the upper quota. And there's some apportionment methods that do follow this rule, like Hamilton's and Lowndes'. There's others that do not follow this rule. Those are called divisor methods, and that'll be in another video. But for now, this is the quota rule, and we're going to be looking at following it. Starting with Hamilton's method, starting with Mr. Alexander Hamilton himself. Hamilton's method says, if you're dividing and you're dealing with these decimals and it gets a little crazy trying to figure out what to do, go ahead and find your standard divisor, and then the standard quota for each group. then take the lower quota of each group. If the lower quotas add up to your total a number of items you can allocate, then you're good. Sometimes that happens and you're good. But if it does not happen, then if you have whatever leftovers that need to be allocated still, give those to groups with the largest fractional parts first. So in other words, look at the decimal parts, and whoever has the largest decimal part, give it to them first, and then make your way through. Okay, for example, another country with 5 states. Let's say that state A has 1,320,000, so it's going to be similar to the example earlier, but the populations have changed. State B has 1,515,000. State C has 4,935,000. State D has 1,180,000. State E has 1,112,000. All right, if you want to see the total population, you add those up. Okay, this time I'm getting 10,062,000 when I add those up. Did I add them up correctly? I'm double checking my copying, make sure I copied the numbers correctly. Okay, so there's 200 seats again. Just adding them up again. Okay. So when you go to find your standard divisor, you're trying to see, well, how many people per seat. So you do the 10,062,000 divided by 200. Okay, I'm going to put that in my calculator this time so I'm not such a mess again. All right, I get 50,310. So for every 50,310 people, one of these seats is going to get apportioned. So that's nice, right? All right. So then we're going to take those numbers and we're going to find our standard quotas. So we're going to have to take, for each of those, we're going to have to take and divide by our standard divisor. So A has 1,320,000 people. We're going to divide that by 50,310. Just so that I have enough of a decimal part to take a look at, I'm going to leave this as, I'm going to carry it out to 4 decimal places, 2, 3, 7, 3. So that later, if I have leftovers, I can definitely see who has the bigger fractional part. State B had 1,515,000 people. And when you go to divide that by the 50,310, all right. So we've got 30.1133. Okay, state C, 4,935,000 divided by 50,310. So we got 98.0918. State D, 1,180,000 divided by 50,000, 310. You're going to find that these lessons, it's a lot of tedious calculations. The math itself isn't hard. It's just time consuming and tedious. Just a fair warning. And it's going to get worse when we get into those divisor methods later. So you're going to see some empty space in my videos because I'm typing things into the calculator and double checking my numbers. It's so easy to make a mistake with this stuff. All right. Okay. So yeah, we definitely got decimals in all 5 states on that one. So we took each state's population and we divided it by that standard divisor to get the standard quota for each of the states. Okay, yep. All right, so we did that. The numbers look kind of familiar because we did before have some answers that were not too far off from what we see here. So we can feel like we're in the right ballpark, even though our population numbers in each state are different, but they're not drastically different. But anyways, okay, I'm rambling, sorry. Okay, so with Hamilton's method, I'm going to say HA for Hamilton's apportionment method. We would first just take those integer parts. That's what it means with doing the lower quota. Like for state A, 26.2373, the lower quota would be 26. For state B, the lower quota would be 30. For state C, it would be 98. For state D, it would be 23. And for state E, it would be 22. But when you add those up, they don't quite add up right. All right, when I add those up, I'm getting, let me do it again on my calculator. 26 plus 30 plus 98 plus 23 plus 22. You get 199. But there was 200 seats to apportion. Remember that? 200 seats. So we have one more seat. So according to Hamilton's method, what we do is we go back and we look at those fractional parts. Let me use a different color maybe. We go back and look at those decimal parts and we decide who to give leftovers to based on that. So we find the one with the largest decimal part first. And that looks like it's state D. Because out of 0.23, 0.11, 0.09, 0.45, 0.10, 0.4546 is bigger than all the others. So state D gets that extra seat. So that now it adds up to 200 seats. So Hamilton's apportionment says state A gets 26, state B gets 30, state C gets 98, state D gets 24, state E gets 22, based on this information and this populations. That makes a lot of sense because state C had the most people by far. They got the most seats still. What state B had the next most people? State A, then it went like by order of population in this situation, this example. And then it went state A, then it went state D, and then state E. So state D got that extra seat. Nice, huh? And that's Hamilton's apportionment. That's how that works. So a little bit about Alexander Hamilton. Add him to your mathematician list. He was the first Secretary of the Treasury, and he and Thomas Jefferson did not get along politically. And he ended up getting in a duel with Thomas Jefferson's vice president, Aaron Burr, and he was not on the winning side of that duel, unfortunately. So lost his life a little early due to that. And his method, even if he had lived longer, he would have probably been disappointed, because after the 1790 census, there were 65 seats in the U.S. House of Representatives to apportion among 13 original states at that point in time. The decision by Congress was to use Hamilton's method at that point in time. President Washington vetoed the decision, and instead they ended up using Jefferson's method. Jefferson, his political adversary. They used Jefferson's method for a while, then they used Webster's method, which we'll talk about in another video. And then finally in 1852, they actually did use Hamilton's method. They brought it back, and they decided to start using it, and they used it until 1900. So Hamilton was not able to live long enough to really see that through, but it did end up getting used for a while. Okay, the second method in this quota method section is something called Lowndes' method. Lowndes looked at Hamilton's method, and he felt like it wasn't good enough, especially when it came to smaller states. Like, Hamilton's method tended to favor larger states, but with the smaller states, it's like those fractional parts really matter. Like, those decimal parts matter a lot more than what Hamilton's method allowed them to. So he wanted to compute something called the relative fractional part to give that a little more oomph. So it's very similar to Hamilton's method in that you find the standard divisor, calculate the standard quota, find the lower quota. But before you divvy up at leftovers, you don't just look at the decimal. You look at the ratio of the decimal over that integer. That's called the relative fractional part. And that can make a difference in how the seats, sometimes it makes a difference in how the seats are apportioned. So Hamilton's method was favoring states with larger population, but Lowndes' method will favor states more often with smaller populations. Because in a smaller state, extra seats are going to be awarded to the state with the largest fractional part, which is going to more likely happen when your integer part is smaller compared to those larger states. So that's, more often it helped those Connecticut and Rhode Island type states. All right, so let's see how it works. We're going to use the same numbers from earlier so that we can compare and see how the seats get divvied up using Lowndes' method. So we're going to go back to state A, B, C, D, E that we just used in Hamilton's method. We're still going to have the same populations from that example. Okay, and we're still going to use the same standard quota, so I'm just going to cheat and go back up here and take a look at what we had. We had 26.2373. Hopefully I'm not making any of you too dizzy. Sorry. That's the way this thing works. Then we had 30.1133. Then we had 98.0918. $23.4546. And then 22.1030. Oops. All right, so that's still, the lower quota was still there with the 26, the 30, the 98, the 23, and the 22. And that still didn't add up, that still adds up to less than what we need it to add up to. But before we make a decision of who gets that one extra seat that's still available, we need to look at those relative fractional parts. So for state A, we take the 0.2373 and we put that over the 26 and see what that comes out to. I get 0.009126923. I'm just going to keep it like long for now. Sorry about that. B, I'm going to take the 0.1133 and divide that by the 30. And I get 0.0037766667. State C, I'll take the 0.0918 and divide that by the 98. Zero point zero 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 936,735. State D. Notice the relative fractional part on state C is a lot smaller. Interesting, huh? Because you're dividing by a bigger divisor there, the 98. 0.4546 divided by 23. 0.019765,217. And finally, state E, we had the 0.1030 divided by 22. So 0.004681818, blah, 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 blah. All right, so this time who had the biggest? I'm going to start looking at these numbers here. And you can see right away that state D has the biggest of those. So state D gets that one extra again. So how does that compare to the apportionment before? 26, 30, 98, 24, 22. 26, 30, 98, 24, 22. Well, turns out we got the same apportionment. So in this case, it didn't really make a difference. But there are scenarios where it does. And I mean, if there weren't, then this would have never been a disagreement about what method to use where. So this one, you kind of see the whole thing, like the bigger population was state C, and notice how state C's relative fractional part was a lot smaller. So you can start to see why like smaller states would tend to get the favor. The really small states were D and E, and D ended up in this case getting the favor. So there's that. That's Lowndes' method. So William Lowndes was a representative from South Carolina and proposed this method in 1822. Again, this is Hamilton's method, just tweaked a little bit. For a smaller state like Connecticut or Rhode Island, that fractional part is going to be a lot more important with their smaller population and hence fewer seats. So this will give them kind of not an advantage, but just give them that chance to get maybe that extra seat that they wouldn't have had otherwise. So both of these methods satisfy the quota rule, but they are questionable. I just, several times now I've mentioned Hamilton favoring larger populations while Lowndes favors smaller populations, but also in particular cases, some other things, some troubling things can arise, and we'll talk about that in a future video. For example, you might increase the items to apportion, like you might be using Hamilton's method, and you might say, oh, you know what? We had 80 desks to hand out to the classrooms, but all of a sudden we were gifted 20 more. But somehow, even if you have those extra desks to divvy up amongst classrooms, you don't change the number of classrooms, but suddenly maybe one of the classrooms might lose desks that they're being allocated. It's very strange. We'll go into example with that later, but strange things like that can happen sometimes with Hamilton's and Lowndes' methods. So there's those other rules that there's other types that we'll talk about with the divisor methods, and that kind of offsets some of the issues that are brought up here. All right, but until then, happy apportioning, and just be patient. Again, the math's not hard. You can use your calculator, but it can be very tedious, and it doesn't hurt to slow down and do like I was doing in the video, where I was like double checking my numbers, made sure I copied things correctly, sometimes double typing things in the calculator to make sure. And even then, I'm sure I might have made a mistake somewhere. Hey, if you ever catch that I made a mistake somewhere, point it out. It can be worth some bonus points to you if you're correct. All right. Well, thank you for joining me, and I'll see you again next time.